The graph above shows the one-dimensional acceleration of an object moving in one dimension for 5 seconds. At time t equals 0, the object's initial velocity is 8 centimeters per second, and its initial position is negative 10 centimeters. Draw the velocity versus time and position versus time graph for the object's motion.
So here we have the acceleration graph, and in order to find the relationship between acceleration and velocity, we need to understand that acceleration is the derivative of velocity. So therefore, when we take the integral of acceleration, we're given velocity. So in this case, when we're given the acceleration graph, we need to find the area under the curve. So here between 0 and 1, we have negative 6. And we do this because the initial velocity is 8 centimeters per second. So we're going to add that to the integral of acceleration between 0 and 1, and then we're going to do it between 1 and 2, and so on and so forth. So here between 0 and 1, we have negative 6. Between 1 and 2, we're going to have 0, because there is no area. Between 2 and 3, we're going to have 4, because here we have 1, and then it goes up 4. So when you do 1 times 4, it gives you 4. And then here, we have 4 again, because you're going to do 4 times 2 divided by 2, because as you can see, this is a triangle, a right triangle. So in order to find that area, you're going to use 1/2 base times height. And then here, we're just going to assume that it's going to be approximately around 2.
So this is what we got for a velocity graph given the areas we've taken from the acceleration graph. So the slope of this first line, which should be acceleration, since acceleration is the derivative of velocity, should be minus 6 centimeters per second squared. So this goes down 6 and over 1. So from 1 to 2 seconds, the slope, which is your acceleration in the other graph, should equal 0, which is why it approaches a straight line across. Then from 2 to 3 seconds, the slope was 4 centimeters per second squared. So therefore, on the interval of 1 second, it increases 4 velocity units. Then once again, from the previous graph shown here, the acceleration ended up being a slope of negative 4. So once you draw it for the velocity graph, since there's a constant deceleration, since the acceleration looked like this, the slope of the line should be approaching a maximum since the graph is decelerating. So this is approximately 4 is the slope, but it has a B-shaped concave down.
So next we have to start graphing the position from the given velocity graph that we just found. So in order to do that, we need to understand the relationship between velocity and position, just like how we did for acceleration and velocity. So as you can see, velocity is equals to the derivative of x, which is the position. So in order to find x, we need to take the integral of the velocity. So in this case, the position of 0 equals negative 10 plus the integral between 1 to 0 of velocity. And we're just going to take this for every single point.
So since position is the integral of velocity, taking that integration from the velocity graph will generate the slope of this graph. So from 0 to 1 second, starting at our initial negative 10 centimeters as given in the problem, the slope should be not a constant form, but it should be 3 centimeters per second. So it goes to negative 7 about. Then since the previous graph has no area below it, therefore the slope must be 0, so it's just a straight line from 1 to 2. From 2 to 3, the slope should be 3 centimeters per second at a constant rate. And then from 3 to 5, since the previous graph approached a maximum and was concave down, this graph should be increasing at a decreasing rate and therefore have a point of inflection at negative 1. Conclusively, problem number 3 demonstrated that acceleration is the derivative of velocity and that velocity is the derivative of position. Also, that means the integral of acceleration is velocity, and thus the integral of velocity is position. So good luck on the test, and thanks for watching problem number 3.